This is what we have discussed in last class. Here on this diagram, we have find out the minimum spanning tree, which is this one, and we found this out by following the Prim's algorithm. This was the given graph, or this was the given network model. From here, we have found out the minimum spanning tree, which is this one, by following Prim's algorithm. Now, today we'll discuss about the cut optimality theorem. Okay, cut optimality theorem basically justifies the Prim's algorithm. Now, it says for every arc ij which belongs to the tree, okay, these are the edges or arcs, these belongs to the tree, each of these arcs belongs to the tree. Now if we take any of these arcs and justify their weight, which will be called Cij, for any ij where the ij's belong to the tree, okay. Now then this Cij, according to the cut optimality theorem, we will write Cij is less than equal to CKL, okay, where these ij's are belong to the tree and this KL in the network model, those are options to join I and j. Okay, now I will show you with an example. This is the spanning tree, okay. In this spanning tree, what I said, that the cost of or the weight of any edges should be less than or equal to the other options, okay. Now suppose we talk about this 2 4, okay. This 2 4 had the maximum weight, which is 8. This 2 4, this edge or this arc belongs to the tree, and this 8 is the weight of this 2 4. Now you look, if the 2 4 is get deleted, okay, 2 4, just imagine it is deleted, okay, then there are separate two positions. First is this 1 2 3 5, and the second is 4, okay. Now you look, to join the 4 into the spanning tree, what are our options? Either you have to join 1 4 or 2 4 or 3 4 or 5 4. So if this 2 4 is imaginarily get deleted, then to join 4 into this spanning tree or into this portion, we have the options to join either 1 4 or 3 4 or 5 4, okay. Now it is said that this C2 4, let me draw it again here. This is 1, this is 2, this is 4, this is 3, and this is 5, okay. They are joined in this way. This is 8, 5, this is 6, this is also 6, okay. Now this was the spanning tree. If these 2 4 get deleted, if we go for choosing another option, now then this C 2 4, which is a arc or edge belong to the tree, should be less than C1 4, less than equal to C3 4, C5 4, okay. Now let us look on the network model. You look, this was the model, this was the model. Here you look, 1 4 is not available, 1 is not directly connected with 4, not available, okay. Now check for 3 4. You see 3 4 is 8, which is equal to 2 4, Okay, so we could have joined 3 4 instead of 2 4. There is no problem, which we have done. We have joined 3 4. We look here in Pushkal's, we have joined 3 4. That is also a minimum spanning tree. Now this can be done because this C24 is 8 and C34 is also 8. So you can choose either of them. Okay, that satisfies the cut optimality theorem. And there is another option which is 5 4. 5 4 similarly, if you look at this model, this 5 4 is also 8. So we can find this C24 is equal to C34 and C54, which satisfied the cut optimality theorem. Similarly, if you look for another edge, say we are talking about say 1 2 here. If we delete 1 2, if we delete C1 2, then this C1 2 must be less than. How can we join these two parts? If the 1 2 get deleted, then we can join these two parts by C3 2, C1 5, C3 5, or C1 4 or C3 4. Okay, these are the options we could have been taken. Now let us check. C1 2 is 5. Okay, C1 2 is 5 here. Look, C1 2 is 5. Now what are the options? The options are here. C3 2, we have written C3 2. We have written C3 2. So let us check. In case of C3 2 here, what is C3 2? Look, 7, which is greater than 5. Now next option is we have written C1 5. Look, C1 5 is not connected. Okay, next option C3 5. C3 5 is 6, which is greater than 5. Okay, so 3 5 cannot be the option. C1 4. C1 4 is not connected, does not exist, which is infinity. And C3 4. C3 4 having 8, which is greater than 5. So our only option is only connecting 1 2 here. So here there is no other option to join these two parts except 1 2. So this satisfied the cut optimality theorem. Okay, did you understood what I was trying to say in cut optimality theorem, or do we need to repeat
নো
it?
স্যার 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 ক্লিয়ারলি স্যার বুঝতে পারছি না স্যার।
মানে আমার অর্থ বুঝতে পারছো না, না আমার মানে এটা টপিকটা বুঝতে পারলে না?
না স্যার টপিকটাই বুঝতে পারছি না স্যার।
Okay, okay, okay. So let us repeat it again.
ইয়েস স্যার, ইয়েস স্যার।
This fan giving me so much trouble today. Okay, just give me a minute. Okay, is this two figure visible properly?
Yes, sir.
Okay, now we have found out the minimum spanning tree. Here what we can see from the Prim's algorithm. Okay, and the cut optimality theorem justifies the Prim's algorithm. Now what the cut optimality theorem says, if you choose any of the arcs or edges from the tree. Okay, so what are the edges here in the tree? We have 1 3, 1 2, 2 5, and 2 4. Okay, so we can choose any one of these. Again, these options are, I mean these edges in this spanning tree are, look carefully, see 1 3, I mean 1 3 is a edge, sorry, 1 3 is edge, 1 2 is edge, 2 5 is edge, and 2 4 is edge. So there are 4 number of edges in the spanning tree. Okay, so the cut optimality theorem says that the weight of these edges, if you choose any of the edges, then the cost of that particular edge, the edge belongs to the tree, will be less than or equal to the KL, the other options which are KL. So the weight of IJ should be less than the weight of KL. I am giving an example here. If we delete 2 4, okay, in this spanning tree, if we delete 2 4, okay, now then the spanning tree divides into two halves. One part is 3 1 2 5, another part is 4. Okay, now how can we join 4 with this part? So 4 either can be joined with 1, either can be joined with 2, either can be joined with 5, or the 4 can be joined with 3. Okay, so the question is, why we have joined 2 4? We have to check the other options, whether they are equal or less or greater. If our joining this 2 4 edge, is it feasible or not, or this 2 4 should be in the minimum spanning tree or not? That is our question, and that is what we will prove with cut optimality theorem, whether 2 4 should be present in the minimum spanning tree or not. The justification of 2 4 being in the minimum spanning tree, that will be done by cut optimality theorem. Okay, so now we are assuming, we are deleting that 2 4. Okay, so the spanning tree divides into two portions. One portion contains 3 1 2 5, other portion contains only 4. Is it clear up to this point? Give me a response.
Yes, yes, sir.
Okay, so now our job is to find 4 with either of these 4 vertices. Either 4 need to join with 1, or we need to join 4 with 2, we need to join with 5, we need to join with 3. Either of the vertices should be joined with 4 to include 4 in the spanning tree. Now here, by following Prim's algorithm, we have joined 2 4, and by cut optimality theorem we will justify that whether 2 4 is optimum or not. So let us check by cut optimality theorem. If we delete 2 4, then what are the options we could have done? So we could have joined this 4 with 1, we could have joined 4 with 3, we could have joined 4 with 5. Okay, these are the three options. If we do not have joined 2 4, then what are the options? We have the options whether we can join 4 with 1, we can join 4 with 3, we can join 4 with 5. These are the three options. Now we will check that 1 4 does not exist, so we cannot join 1 4. If we join 2 4, then the weight becomes 8. If we join 3 4, then also the weight becomes 8. If we join 5 4, then also we could have we can get the weight 8. So if we join 3 4 or 5 4, the total weight of the minimum spanning tree would be remain unchanged, because 2 4 is also 8, 3 4 is also 8, 5 4 is also 8. So our cut optimality theorem says C2 4 should be less than equal to C1 4, C3 4, C54, and that is satisfied here. Is it clear now?
Yes, sir.
Okay, now on the same spanning tree, we will repeat for another arc. So let us have 1 2. Okay, we can delete 1 2. We will justify that whether joining 1 2 is feasible or not, is optimum or not. That is the question. So if we imaginarily delete 1 2, then this minimum spanning tree, this one divided get divided into two portions. One portion is 1 3, 1 and 3, and the other portion is 2 4 and 5. Okay, so what are the options? Whether we can join 2 3 instead of 1 2, we can join 2 3, we can join 1 5, we can join 3 5, we can join 1 4, we can join 3 4. So if we do not join 1 2, and if we try for other options, so then there are almost 5 options: 1 5, 3 5, 3 2, 1 4 and 3 4. There are 5 options to join these two portions except 1 2. So let us check all these 5 options. Okay, so first we will check with 2 3. If we look at the model, the 2 3 is 7, which is greater than 5. So if we join 2 3 instead of 1 2, then the length of the spanning tree will be higher than 25. So that will not be a minimum spanning tree. So that's why we cannot join 2 3. Okay, now let's go to 1 5. There is no connection between 1 5. So the length of the or the weight of the edge 1 5 will be infinite. So there will be no direct linkage. So 1 5 does not uh, follows the satisfies the condition. Okay, the next 3 5, 3 5 having weight 6. So if we have joined 3 5 instead of 1 2, then also the minimum spanning tree will have the total weight is more, which is 25 plus 1 26. So that is not be a minimum spanning tree because 6 is greater than 5. So similarly, we now check for 1 4. 1 4 does not exist. 1 is not directly connected with 4. Okay, so there is no option to join 1 with 4. Now we could have joined 3 4. So if we join 3 4 instead of 1 2, then the weight will be 8 instead of 5. So if we join 3 4 instead of 1 2, then the spanning tree weight will be higher. That will not be minimum spanning tree. So to be the minimum spanning tree, the 1 3 portion and the 2 4 5 portion, these two are different portion, should be joined through 1 2. So this cut optimality theorem is now satisfying the Prim's algorithm, justifying the Prim's algorithm. So is it clear?
Yes, sir.
Okay. So now next we will go to path optimality theorem. Here we will check the optimality. And you will find that it directly justifies the Kruskal's algorithm. It says for every non-tree arc, for every non-tree arc, the options in the tree should be individually less than that the weight of the non-tree arc. So let us understand with example, because the theory is quite difficult. Uh, so this is the output or the minimum spanning tree from the Kruskal's algorithm. Here, if you look 2 3, which was connected in the network model, look at 2 3, look at 2 3, this is connected with weight 7 is connected in the network model, but this 2 3 is not present in the minimum spanning tree. So this is a 2 3 is a non-tree arc, okay, which is not included in the tree minimum spanning tree. So 2 3 is a non-tree arc. Now if we join 2 3, we get the weight 7. What are the other options to join 2 3? What is joining 1 2 and 1 3? Okay, if we join 2 3, that will be a non-tree arc, and there are two arcs which are present in the tree, which are 1 2 and 1 3, which are joining this 2 3. Okay, so this 5 and 6 both are individually lesser than the non-tree arc 7. So this Kruskal's algorithm is justified by the path optimality theorem. Is it understood?
sir.
Okay, so
আর
this,
একবার বলবেন এটা
হ্যাঁ বলবো,
বলুন
this 2 3 is not present in the minimum spanning tree found by the Kruskal's algorithm. Okay, but you look at the problem figure, this 2 3 is present in 7 with weight 7 present in the network model. This is the 2 3 arc which is present in the network model with weight 7 but not present in the minimum spanning tree found by Kruskal's algorithm. Okay, so the path optimality theorem says that the option in the tree joining these 2 3 are 1 2 and 1 3. 1 2 having weight 5, 1 3 having weight 6. This 5 and 6 both are individually smaller than the arc 2 3, which is the non-tree arc having weight 7. So 5 and 6 are lesser than 7. So this is how it justifies the path algorithm, satisfied the path algorithm, and justifies the Kruskal's algorithm. Is it okay now?
Yes, sir.
Okay. Okay. So now we will learn a very interesting algorithm to find the shortest path. Suppose you have a network model is given and you need to know the minimum path to connect from the starting node to the end node. Okay, there are different problems on the shortest path problems, like you may choose to start with the most fast node and you can reach to the extreme last node, or you can start from the start node, or you can find the shortest path to any of the nodes, or you can start from any of the nodes and you can get the distance from any other nodes. Okay, so there are types of shortest path, but here in this class we will learn how to find out the shortest path from a given start to a given end, or the extreme start to the extreme end. Okay, and for that we will learn an algorithm which is called Dijkstra algorithm. Okay, to find the shortest path we learn Dijkstra's algorithm. Okay, this is a very interesting one. uh, Before we start Dijkstra's algorithm, we will discuss a very easy network model, very easy one, so that I can imply it on the bigger network. So let us have a very simple network. Okay, what we have is three nodes and two arcs. Okay, now here from 1 to 2, if you want to reach, suppose these are time or distances. So if we want to reach from 1 to 2, we need to uh, expense time or distance say 4 amount. Okay, now if you want to reach 3, there is no path to reach from 1 to 3, so we write infinity here because there is no direct path. Okay, now as we again look at 2 and we find the options from 2, then you see it is already 4 here. Now this 3 from 2 will be taken only 4 plus 2 6, so this infinity will be replaced by 6. So this is how what we are actually doing, we are relaxing the nodes. This method is called relaxing. Okay, the term is not so important. What is important is to know the procedure. Okay, when you started from 1, there is no path up to 3, that's why we have written infinity. Now when we started from this node 2 and the time taken is 2, so here the time taken is 4, so 4 plus 2, here it is 6. Now we have found out a way to reach 3 from 1 is going to take 6, and 6 is lesser than infinity, so that's why we updated it with 6. Okay, this is the method we will remember. Now let us discuss for a little complex problem. Not much, very little. Okay, so let us a network like this. Okay, so this is the network. Now here we'll start with 1. This will be our start node, and we need to reach 6. Okay, so we need to find the minimum or the shortest path to reach 6 from 1, and for that we will write a table. Now in this example we have written just above these digits. Here we will not write this above the digits. Okay, what we will write is in a table. So we will draw a table. We'll start with 1 and we will find out what are the options here. 2, 3, 4, 5, 6. These are the nodes. We start with 1. If we start with 1, then we can reach, okay, these 2 are not given. This is 2, this is 4. These are weights. Now if we want to reach 2, it will take say 2 days or 2 hours. If we want to take 3, then the weight to be passed 3, and 1 is not connected with 4, 5 and 6, so here we'll write them as infinity. Okay, now we look here. What is the minimum? The minimum is 2. If the minimum is 2, then this 2 gets selected. 2 gets selected. Now from 2 we can reach 3. Is 2 plus 1, so this will be 3. Okay, so why I am writing 3? Because 3 is lesser than 4. Initially we were reaching initially we are reaching 3 at time required, or days required, or distance required was 4. Now we have found another way. By 1 2 3 method we can reach at 3 meter or in 3 seconds. So 3 is lesser than 4, so this 3 is updated by 3 instead of 4. Next, this 2 can reach to 4 by, here it is 2, so 2 plus 7 at 9, which 9 is lesser than infinity. That's why we are updating it as 9, and 2 is not connected either 5 or to 6, so this will remains infinity and infinity. Okay, 2 is already selected here, so here no need to write it again, or you can just update by 2 by putting the same value. So here we have 3 is minimum, so 3 gets selected. Okay, so we have reached up to 3. Now from 3 there is only option to 5. So here the weight, I forgot to write the weight here, is 3. Okay, now so if you want to reach from 3 to 5, we can reach 3 at 3 second or 3 hour, so we can reach 5 at 6, which is lesser than infinity, so it get updated, and 3 is not connected to any of it. Okay, so we will mark it, and we will choose the 5, and we'll write here 5. Okay, now from 5, 4 is connected, and the time is here is 6 at 5, so at 4 it will be 8. Initially it was 9. 9 will remain as it is, and these will also remain as it is because they are not yet selected. That's why they will remain as it is. Now when 5 is selected, so 5 plus 2 we get 7, but initially the 4 was 9. Now we are getting a new path which is 7. Okay, so this get updated, this is already selected, and from 5 to 6 it takes 6 plus 5 becomes 11. Okay, now among these two, this is 7 minimum is selected, so we'll select 4. The node number 4 will be selected. Okay, now we look at 4. To reach 4 we require 7 days or 7 hours, or 7 meters is the distance. Okay, either this is the weights are in distance or in times, so these are the weight. So to reach 4 we require the minimum weight 7. Now we start from 4 and this goes to 6. So 4 goes to 6 and here it is 7 plus 1, 8. So 6 get updated by 8. So initially it was 11, now it is 8. So finally the 6 is selected. So is the path to reach 1 to 6 in the shortest path will be 1, 2, 3, 5, 4, 6. This is the shortest path. So is the method clear to you?
Sir,
স্যার একটু রিপিট করলে স্যার ভালো হয় স্যার।
Okay, listen up. The algorithm is called Dijkstra algorithm. Okay, here our job is to reach from start node to end node at the minimum path or the shortest path with minimum weight. That is our objective. Now here we'll start with 1, so 1 is get selected at first and we will write out the other nodes in this row. So other nodes are 2, 3, 4, 5, 6 as it is here. Now 1 is connected with 2 and 3. To reach 2 from 1 we require 2 days. Okay, so or the distance is say 2 kilometers. Okay, so 2 is the weight to reach from 1 to 2. That's why from 1 to 2 we have written 2. Okay, from 1 to 3 it requires 4, the weight requires 4, so we have written 4 within 1 3. We have taken 4 and 1 is not connected directly connected with 4 5 and 6, so below 4 5 and 6 we have written infinity. Okay, so among this row 2 is minimum. 2 is minimum, so 2 is selected and 2 is taken out. Now we look at 2. Okay, so from 2 we look at the options. It is connected with 3, so the weight required to reach 3 is 2 plus 1 3, but previously we have found 4. Now we are getting a new way to reach 3 at weight 3, which is lesser. So this is why this 4 is getting updated with 3. Okay, and this 4 initially was not connected at infinity distance or infinity time required. Now this 4 is connected with 2 plus 7 at 9. So that's why 9 is being updated. 9 is lesser than alpha, so 9 is being updated. And the rest of the nodes 5 and 6 are yet not connected, so that's why 5 and 6 are infinity. Okay, now in this row 3 is minimum, so 3 is connecting to node 3, so node 3 is selected. Node 3 selected. Now we will check connectivity from node 3. So node 3 is connected only node 5. So here we can reach node 3 at a distance of 3 or at a time of 3. So weight required is 3 to reach 3. So 3 plus 3, 6 is required to reach 5. So initially to reach 5 there was infinity weight required. Now it is required only 6. So 6 get updated. And from 3, 4 is not connected, but to reach 4, 9 weight is required. So 9 is kept as it is and 6 is not connected with 3. So 6 is as it is, infinity. Okay, now in this row 6 is minimum, so 6 corresponding to node 5, so node 5 is selected. So when node 5 is selected we go to node 5 and time taken to reach node 5 is 6. We'll remember that to reach 5 time the weight required is 6. To reach 4 from 5 we have to take this direction of the arrows very carefully. So to reach 4 we can get weight 8. 6 plus 2 8. Initially it was, when we are at 4, initially it was 9. You see, this was 9. Now we have found out a way to reach here. 6 plus 2 8. Sorry, this will be 8. I have made a mistake here. So when we select 5, from 5 to reach 4 it requires 6 plus 2 8. So new weight required is 8, but previously it was 9. Previously it was 9, now it is 8. So this 9 get updated by 8. Okay, and from 5 to 6 it takes 6 plus 5, 11. Okay, so in 11 previously 6 was not connected, so we have taken infinity. Now 11 weight is required, so this infinity get updated by 11. Okay, now between 8 and 11, 8 is minimum, so 8 is chosen, and 8 is corresponding to node 4, so node 4 is taken here. So from node 4 we will check this 8 plus 1 is 9. This 8 plus 1 is 9. Previously to reach here is taken 11, but now it is 9. This got increased. So 6 plus 2, 8, 8 plus 1, this is 9. Previously it was required 11, now it is required 9. So we will connect 6 from 4 only. So that's why we'll taken 6 at the end. So the path is 1, 2, 3, 5, 4, 6. 1, 2, 3, 5, 4, 6. And we will connect this path this way, and we will write the answer that this double arrowed path is the shortest path to reach node 6 from node 1. Is it clear now?
Sir.
Okay, then any more questions on this topic? Okay, no questions.
হ্যালো স্যার
Yes,
হ্যালো স্যার এই 3 নোট থেকে এই আমি ক্যালকুলেট করছি কেন এই 546 এটা বুঝতে পারলাম না
কোনটা থেকে একটু ক্লিয়ারলি বলো।
এই 3 নোট যখন আমি 3 নিচ্ছি 1 2 3 3 পর আমি যখন ক্যালকুলেট করছি পয়েন্টটা 3 থেকে নিচ্ছি এটা কেন করছে আমি বুঝতে পারলাম না
আমি এখানে তো 3 পয়েন্ট সিলেক্ট করে নিয়েছি বিকজ 3 is minimum of
হ্যাঁ
this. Okay,
ওকে
3 got selected, so that means now we have chosen the shortest path to reach 3. Now we will start from 3. Later we have taken 5, so then we have taken the paths to connect 4 with 5 and from 5. So when we select one, then we will collect, we will advance selecting that method. So initially we have selected 2. Now when we have calculated, we have started from 2, then we have selected 3, then we have selected from 3, then we have selected 5, then we started from 5. This is how we will advance. Is it clear now?